Today, we'll be finding pH of weak acids and bases, particularly using Ka, buffers, and ice tables. Let's get to it. Strong acids dissociate completely in water. So for example, if we started with 2 molars of HCl, 100% of that would dissociate in water. So we would end up getting 2 molars of H+, and 2 molars of Cl-. But what about weak acids, such as acetic acid?
It turns out that they have very low dissociation. So for example, if we start with 2 molars in water, the concentrations of the dissociated parts are way lower. Specifically, it will be 0.006 molars. And I know this because of this thing for weak acids called the Ka. It stands for the dissociation constant, and it tells you how much the weak acid likes to dissociate in water. Its equation is written like this, where Ha is the weak acid and the A- is the conjugate base. So let's say we started off with 2 molars of the weak acid. The Ka for the acid is usually given to us in the problem. For acetic acid, this number happens to be this. Next, we know that our Ha is 2 molars, so we'll plug that in. But now we have a problem. We have 2 variables, A- and H+. So how do we solve it? The answer is that we know that these numbers are equal, because for every COOH that breaks, you always get 1 H+ for each COO-. So since they are equal numbers, we can just set both of them equal to x. Now let's get the value of x. To do so, we'll multiply both sides by 2, then take the square root of both sides, which gets us this value. And as a recap, when 2 molars of the weak acid, COOH, is thrown in water, we get X amount of H+ and X amount of COO-. But this is not 100% accurate. If we start with 2 m's of COOH and some broke up into H+ and COO-, that's how much we need to subtract COOH by so that the total gets us 2. So when we do that, we get a number that is very close to 2. So it really doesn't matter. The difference is pretty negligible. What I mean by that is this. In the Ka equation, for Ha, we can either put in what we had before, which was 2, or this 1.994 value. In both cases, our answer will round to the same number, 1.8 times 10 to the negative 5th.
So why do we care about how much of the weak acid dissociates in the first place? That's because if we find out how much H+ is going to be produced, we can easily find the pH by plugging it in into the negative log equation.
Which, once we plug in our value, we get our answer. So overall, when 2 molars of acetic acid is placed in water, the pH of the solution is 2.22. Now let's focus on the Ha, which is our weak acid, and the A-, which is the weak acid with a missing hydrogen. This is known as the conjugate base. When there's a mixture of these 2 guys in solution, it's known as this term called a buffer. In problems, you might have an example where you have some amount of the H+, which you can identify by either the name, because it ends with ic acid, or from the formula, which always ends with an H. And for the A-, it ends with an 8, with its formula having 1 less hydrogen and a negative charge.
Before we move on to the next portion, if you haven't liked the video or subscribed to the channel yet, please do so.
Also join me at nicoscience.com. Here you can find my tutoring website where you can book a session in this button below and choose from a range of subjects from biochemistry, physiology, biology, chemistry, and genetics.
Alright, back to the video.
So let's do an example. What is the pOH of a 0.802 molar solution of benzoic acid? And we're given the Ka. Since we're given a Ka value, we know we're dealing with a weak acid. The ic acid suffix is a sign that we're starting with Ha. First step is to write out our Ka equation. We know that our Ha is 0.802 and our Ka value is given. Next, we know that for each Ha that dissociates, we produce equal amounts of H+ as A-. So since these values are equal, we can set both as x. Next, let's find x. So multiply both sides by 0.802 and take the square root of both sides, which gets us this value. So this x is not only the amount of A- we have, but more importantly, the H plus concentration, which we can plug into the pH equation, which gets us this value. Finally, to find pOH, we know pH and pOH always adds up to 14. So after plugging in our pH, we get the answer of 11.85. Let's try another example. A 1.2 molar solution of HCOOH has a pH of 1.95. Calculate Ka for HCOOH. Ka indicates that we're dealing with a weak acid, and since we don't see a negative charge, we know that this HCOOH is our HA. First, write out the Ka equation. We'll come back to this later. We know our pH is 1.95, which is equal to the negative log of H+. Next, let's isolate the H+. We'll move the negative over, and to get rid of the log, we'll take the base 10 of both sides. This gets us this concentration for H+. And remember, for every H+, there's an equal number of A-. So we can set both to X. And when we do so, what we have left is to find the amount of HA. To get this, let's use the ICE table. The first step is to write out the equation for the dissociation of HCOOH. Next, we'll put in our ICE. First, we know that we start with 1.2 molars of HCOOH and none of the conjugate base or H+. Next, we know that at the pH of 1.95, our H+ increased to 0.011. So our change in H+ is that value. This number is the same for the molecules on the same side of the equation, and the sign is flipped for the other side of the equation. When we factor this change value for HCOOH, we get this value. And this is our HA. So we'll plug this into our Ka equation, and that gets us our answer. Let's do our final problem. A 1.53 molar solution of acetic acid is 3.5% dissociated. Calculate the pH of the solution. Here's our HA, and when it states 3.5% is dissociated, that just means the amount that is in the A- form. And we know that for every A-, there is equal parts of H+. So when we find the H+ concentration, we can plug it into the pH equation. First, let's rewrite the 3.5% to a decimal and multiply by the molars of the acid we originally had to get us this value. And finally, we'll plug that into the pH equation and we get us our answer.